Welcome to the seminar. We have Professor Thomas Kruijer, especially from America, arriving at Berlin only 6 months ago, and even this talk. I mean, this talk is his. I would say his specialty, right? I mean,
yes. Yeah.
So we are more or less like a original story from the horse mouth. Okay, Thomas. Sorry, so to say that you're a horse, but go ahead.
that is okay. That is fine. Can you all hear me? Is it clear, the sound? Okay.
I can hear you.
Yeah. So first of all, thanks a lot for inviting me today. I appreciate it, and thank you for coming. So I have been asked to kind of deviate a little bit from the moon and give a somewhat broader talk about the early solar system, and basically the stages or the period in the solar system that has led up to the formation of the moon. And I'm particularly going to show you how you can use isotopic constraints to understand the early evolution of the solar system. So we will actually cover a rather broad range of topics here. So bear with me, but I think it makes sense to kind of give a broad scale overview of how you can use isotopes to understand the early solar system. I thought I would start off showing you an image of the solar system today. So because this is what we have, this is our planetary system. Obviously, as you all know, it consists of 4 terrestrial planets in the inner solar system, including the Earth and Mars, and 4 gas giant planets in the outer solar system, including Jupiter and Saturn. And in between is something that's known as the asteroid belt. It's a belt with a lot of small bodies known as asteroids. And these formed even earlier than the terrestrial planets. And this is where we think that most meteorites in our collection stem from. And the big question, at least from my point of view, is how do we arrive at this? What are the processes and events leading up to this system that we see here? And we have a general understanding of this. We generally think that planetary systems form, that the formation of these systems starts with so-called protoplanetary disks. This has been theorized for several decades, actually longer than that, but we know quite a bit about this for several decades. And more recently, these disks are also observed actually using astronomical observations. For example, like this image shown here on the left, this is an image of HL Tauri. It's a young star, and you see that it is surrounded by this gas-dominated disk that's where planet formation is thought to take place. And it is thought that this image probably represents that this stellar or solar system has an age of about 1 million years. Now, so we think that planets start form in such a setting. And we also have a general idea of what then subsequently happens, of how this system then evolves. So we start off with a gas-dominated disk of gas and dust, and this dust then starts agglomerating. This is shown here to the right. And at some point, the first planet-like bodies form, so small bodies, also known as planetesimals. These then collide to form larger bodies, also referred to as planetary embryos. And in the end, these bodies collide through several giant collisions to form the terrestrial planets that we know today. Obviously, the evolution of the outer solar system, which consists of gas giant planets, is slightly different. But this is a general framework which we think is more or less correct. At the same time, there are still a lot of open questions, and there's a lot of research going on in disentangling the exact processes and events that happened in these stages. And also, there are a lot of questions about how quickly does this all happen. And in this talk, I would like to focus on 4 key questions that are important from my point of view. And the first is, when did solar system history start? The second is, when and how did the first planetesimals accrete, so the first small bodies? The third is, how did the large-scale evolution of the solar protoplanetary disk look like? And the last question, and I realized that there have already been some talks about this, but I would like to briefly provide my point of view of how the Earth's moon formed. And that's the end of the talk. I pointed this out in red to indicate that it's slightly different compared to the other topics. And what I would like to demonstrate to you or convince you of that isotopic studies of meteorites and lunar rocks are very helpful in resolving these questions. Okay. And why is this? Why are isotopic studies so useful? Well, they allow us to reconstruct the earliest evolution of the solar system and planet formation as a function of time and space. We can basically build a kind of a map of space and time for these first millions to up to tens of millions of years of solar system history. And what we particularly get, or the two important ingredients that we can learn or that we can gather from meteorites are radiometric ages, which allows us to study the timescales of events, and so-called nucleosynthetic isotope anomalies. And these allow us to study the genetic heritage or genetic links between different materials. And if you use these two, combine these two constraints, and also combine them with other observations and theory, we can integrate cosmochemical constraints with large-scale models of disk evolution and planet formation. That is kind of the ultimate goal. And particularly due to analytical advances over the last decade or so, this has become easier or more and more readily possible. Okay. Now in this talk, of course, I will discuss two classes of meteorites, basically two broad classes of meteorites. There are many different types of meteorites. I will not go into detail about that, but very broadly speaking, I will discuss what is known as a chondrite or a primitive meteorite. That's shown to the left here. This is an example, I think. It is Murchison or Allende. And these are basically, you can view them as cosmic sediments. They are basically agglomerates of different components that formed at different times and at different places in the protoplanetary disk. And the key characteristic of this is that these components, they basically have been clumped together, but they have never melted. So they're still intact in a way, at least for some of these chondrites. And then the other broad class that I will discuss are differentiated meteorites. And these are very different types of meteorites because they stem from meteorite parent bodies that underwent some degree of differentiation, some melting and either metal silicate differentiation or silicate differentiation in the mantle of a body. And an important class of such meteorites that I will discuss today are iron meteorites. And these are metallic meteorites that are thought to stem from protoplanetary cores. So these are actually the only known samples that we have that stem from the core of a body. And in that sense, they're very important for studying core processes and the evolution also even of the Earth's core. Now let's start with the first question. And actually, this is the shortest one that I will discuss today. I only have one slide about this. And this is, when did solar system history start? And we think we know this actually quite well. This is relatively well established. And if you take some of these chondrites and look at them in detail, they contain components known as calcium alumina-rich inclusions. So in here to the left here, there's an image of such an inclusion, a white inclusion you see here. They're micrometer to centimeter size. And they consist of minerals that formed at very high temperature under very high temperature conditions. Some of them are even direct condensates out of a hot nebular gas, so it's thought. And the good thing about them is that they can be very well dated using some decay systems, including the long-lived uranium-lead chronometer. And this is, so they can be precisely dated using this system. And how this works is, I will not go into detail about this, but basically the summary plot is shown here to the right. This is a lead-free isotope plot, showing you different isotopes of lead, and you can measure different components of such an inclusion and obtain a so-called isochron. And if you then calculate the slope of this isochron and the intercept, you can obtain an age. And the age that is consistently obtained for CAIs, calcium alumina-rich inclusions, is an age of 4.567 billion years. And this age is the oldest age that we've obtained for any object that formed in the solar system so far. And therefore, they are thought to basically date the start of solar system history, at least from a cosmochemistry point of view. There may be some evolution before, some astronomical evolution leading up to this event, but this is the event that cosmochemists use to reference everything to. This is our anchor point in time at the beginning of solar system history. And as you can see, it's an age that's relatively easy to remember. It's simply 4.567. It's an easy number. So we've solved that question, and we will move on to the next topic. And this is, when did the first planetesimals form? So the first bodies. And this is a very important step. It's a notoriously hard step because it is very hard for several physical reasons, it's very hard to form, say, kilometer-sized bodies. The main reason being that you need to overcome a certain barrier known as a meter-size barrier, where material is rapidly lost to the sun due to inward radial drift to such a disk. So this is something that is, for the longest time, was not very easily understood. Now, we can use isotopic ages of meteorites to provide some constraints on when this then happened. And for this, I use another, I've done a lot of work on this myself, actually. And one way of doing this is using the so-called short-lived hafnium-tungsten chronometer. This is contrary to this other isotope system that I just showed you. It's a short-lived system. It's an extinct chronometer. And it's a decay system in which an isotope of hafnium-182, decayed to tungsten-182 with a half-life of about 9 million years. So this decay is not happening at the present day anymore, but only happened very early on in the history of the solar system. For this reason, it's completely useless for obtaining absolute ages of meteorites, but you can obtain very precise relative ages with the system. Now, the other good thing is that both the parent and the daughter nuclide are so-called refractory elements. So they they have high, basically, melting temperatures, and they are not affected by volatility-related processes. So they occur in chondritic relative proportions in planets. And what we make use of in this system, what we mostly make use of, is of the fact that hafnium is a lithophile element. It prefers the silicates, and tungsten is a siderophile element, and it prefers the cores. So if a core forms after a bulk planet has accreted, shown by the blue body here to the left, the mantle will develop a high hafnium-tungsten ratio, and the core a hafnium-tungsten ratio of about 0. And this fractionation is exactly what you need to date a process like core formation. You need a fractionation of the parent-to-daughter ratio. And if core formation then occurred when this isotope of hafnium, 182 hafnium, was alive, then the mantle and the core will evolve to distinct 182 tungsten compositions over time. And you can use these different isotopic signatures to infer model ages of core formation. So you can directly date core formation using this decay system. And it's been widely used for doing that also. Now, in case of iron meteorites, the case for doing this is relatively simple. And this is shown in this diagram. It looks complex, but it is simple. Trust me. This is a tungsten isotope evolution plot of 182 tungsten over time. So this is time after CAI formation. You see already that we reference again to CAIs. And this black line is an evolution line. And plotted on the y-axis is the 182 tungsten composition. So that's the measured composition of an iron meteorite, expressed here in the so-called epsilon unit notation. This is the parts per 10,000 deviation relative to the terrestrial mantle. This is typically expressed relative to the Earth because that's our reference point, and that is also, for analytical reasons, very useful. And they're expressed in parts per 10,000 because the variations are typically relatively small. And what you can do is just measure the tungsten isotope composition of an iron meteorite and project this on an assumed chondritic evolution line for a reservoir with a chondritic hafnium-tungsten ratio, and then basically read off the age and obtain so-called two-stage model ages for core formation. Now this is the approach. And this works actually quite well. The actual work is actually quite convoluted, and it requires a lot of analytical work in a lab. And just as an aside, I thought I would briefly highlight this. So what we typically do is we take about gram-size samples, we dissolve them in a clean lab setting, so a low blank clean lab with very clean air. They're dissolved in mineral acids in small Teflon beakers. And then the element that we're interested in this case tungsten, is separated from all the other elements using different techniques, usually ion chromatography. And then this purified tungsten fraction is brought to a mass spectrometer, an isotope ratio mass spectrometer, and then the isotope ratios are measured on this instrument. And this can either be done by TIMS, thermal ionization mass spectrometry, or MCI-CPMS, multi-collector ICP-MS. And these instruments are basically the state-of-the-art for high-precision isotope analysis of bulk samples, which we also would use for iron meteorites. Now let's have a look at some results. And I'm taking a few leaps here, but I basically show you the final result of what we obtained for so-called magnetic iron meteorites. And these are the iron meteorites that stem from planetesimal cores, or from the cores of small bodies. And plotted here are data for different iron meteorite groups, I think about 10 different groups. And each of these groups is thought to represent one parent planetesimal. And these are plotted here are these so-called two-stage model ages of core formation. And you see that the ages that we obtain are very, very old. These iron meteorites, these hafnium tungsten ages are between about 500,000 years and 3 million years after CAIs. So this means that core formation on the iron meteorite parent bodies happened a very, very long time ago, at the earliest stages of solar system history, definitely in the stage of the protoplanetary disk. Now, core formation obviously is not exactly the same as the formation of the body itself. It always happens after the primitive body has formed, or it kind of goes hand in hand. And in order to melt and differentiate the body, you need a heat source. And there is basically consensus at this stage that the decay of another short-lived nuclide, alumina-26, was a very potent heat source for differentiation or for early accreted planetary bodies. And we think that this decay system led to melting and then core formation on these bodies. And if you then do some modeling and calculate the time interval between accretion and core formation, you can infer that these iron meteorite parent bodies must have accreted even earlier, within less than 1 million years after CAIs. So this is pretty strong evidence that magnetic iron meteorites derived from some of the earliest planetesimals that formed in the solar system. And this is the strongest evidence that planetesimal accretion occurred very rapidly. So I arrive now at the first conclusions of this talk. So I will slowly fill up this slide through this talk. The first conclusion is that CAIs formed at 4.567 billion years, and this is time zero in cosmochemistry. And iron meteorite parent bodies accreted within less than 1 million years after CAIs, demonstrating that planetesimal formation started very early. Okay, so far so good. We've dated these two events in the solar system. So what can meteorite now tell us about the large-scale evolution of the protoplanetary disk? And for this, we need to add the second ingredient that we can learn about. And these are this is the genetic heritage of meteorites. Now, for this discussion, I thought it's useful to point out something about the general structure of the protoplanetary disk, because as I already alluded to at the beginning, we basically have a bimodal structure in the solar system. The solar system consists of an inner solar system region, which is mostly relatively dry and consists of terrestrial planets, rocky planets like the Earth, Mars, Venus, Mercury, and also the Moon, of course, and several meteorites, parent bodies. And then there's the outer solar system consisting of gas giant planets. And this is a much larger region and also much colder. It's beyond the so-called ice line. There's much more water present. And basically, there are these two broad regions in the solar system. And it would be very great to know if you could pinpoint where exactly meteorite parent bodies formed. Now, fortunately, we have a tool for this. We can somehow have some broad idea nowadays about where in the solar disk the first planetesimals accreted. And this can be accomplished by determining the genetic heritage, so basically the DNA of meteorites, so to say, using their nucleosynthetic isotope signatures. And I will show you how this works in the next few slides, and also some of the big discoveries that have been made over the last few years. But first, what are nucleosynthetic isotope signatures? They are small-scale isotopic variations between different meteorite groups, either bulk meteorites or meteorite components, or even pre-solar grains. And they are basically, the magnitude of these variations is relatively small, in the order of several parts per 10,000 in the isotope ratio. And they ultimately result from the fact that the solar system was heterogeneously distributed in pre-solar carrier phases. That's what we think, at least. And ultimately, this reflects that the solar system was not just one mix of material from different stellar sources, but it means that the material that the solar system comprises material from different stellar sources, and these sources mixed relatively well, but not completely. And this has led to residual isotopic variations among meteorites. Now, we can make use of this fact when studying meteorites, because for assessing genetic links between meteorites. And this in turn may provide us information about mixing and transport in the protoplanetary disk and about its dynamical evolution. So that's what these isotope anomalies are used for. Now let's have a look at some actual data, because this is kind of the theoretical part. Let's now have a look at what we actually find when we look at meteorites. First, let's point out that nucleosynthetic isotope anomalies, they're widely observed in bulk meteorites. So if you take a bulk meteorite sample of, say, about 0.5 gram or 1 gram, it is many different meteorite groups show nucleosynthetic isotope variations relative to the Earth and relative to each other. And if you plot these variations, you can end up with something like this. This is a diagram of epsilon 50 titanium versus epsilon 50 for chrome. So again, parts per 10,000 deviations relative to the Earth. And the two tracers that are used here are the neutron-rich isotopes of titanium, 50 titanium, and chrome, 54 chrome. And you see that different meteorite groups that are plotted here, so different chondrite groups, different achondrite groups, they all show deviations in these isotopic signatures relative to the Earth, which by definition plots here at 0. So that is indicating that each of these bodies has a slightly different mix of pre-solar carrier phases in its genetic makeup. However, there is an even more important observation to be made here, and that is that when you take all the meteorite parent body groups, or all the meteorite groups combined, you see that two clusters emerge in this diagram. And there is a cluster here to the lower left, which the Earth is part of, and the Moon, and Mars, and ordinary chondrite parent bodies, and stellar chondrite parent bodies. And then there's a cluster here to the upper right, which mostly consists of carbonaceous chondrites, as well as some achondrites. And based on this, it has been concluded that we can speak of a genetic dichotomy between so-called non-carbonaceous and carbonaceous meteorites, NC and CC meteorites. And the basic observation that can be made based on this diagram is that there was no mixing, or at least not very efficient mixing, during the formation times of these meteorites, during the times that these meteorite parent bodies accreted. Now there's a different way, and what I should say about this, sorry, this I think is a very crucial observation about the early solar system. It's a very fundamental observation because it comprises all different meteorite groups that we know of. And even more compelling evidence can be obtained if we study another isotope system, and these are molybdenum isotopes. And the reason that molybdenum isotopes are so useful for looking at these characteristics of meteorites, at this dichotomy, is that molybdenum isotopes can be measured in almost every meteorite group, and they can also tell us, provide very detailed insights about the genetic makeup of meteorites. And this is because they allow us to distinguish between so-called R process variations and S process variations. And these are different nucleosynthetic processes, basically. So R stands for rapid process of stellar nucleosynthesis, with which is mostly associated with kind of high neutron fluxes, so processes like supernovae. And the S process stands for slow, and this is associated with a calmer environment and maybe associated with stars like HEB stars. And what you see is that in a diagram of epsilon 95 versus epsilon 94 molybdenum, these two different nucleosynthetic processes, they generate slopes with different lines with different slopes. So you can distinguish between R process variations and S process variations. And this then provides very detailed insights into the genetic heritage as well as into mixing processes among meteorites. Now let's have a look at some actual data. And I'm now plotting in data for primitive meteorites, for chondrites. And you see, and I color-coded these with the same colors that I use in this diagram of titanium versus chrome. And you see that the carbonaceous chondrites plot here in the upper part of the diagram, and enstatite and ordinary chondrites in the lower part of the diagram. So there's already a bit of a clustering emerging. If we now add iron meteorites, so the samples of protoplanetary cores, into the same diagram, you see that two different trends emerge, basically two different lines. And you may remember this from kind of the theoretical slide I showed you 2 slides back. This must mean that we can speak of two different S process mixing lines. If we add achondrites, by the way, to this, the picture becomes even more clear, and you see that there are very clearly two lines, an NC line and a CC line. So this dichotomy extends to iron meteorites and achondrites. It's seen from, and obviously also to molybdenum isotopes. And what you see is that each reservoir has clear S process variations within this reservoir, as we've also seen for chromium and titanium. But there is a clear offset between the lines, and this is probably an R process signature. So the CC reservoir was homogeneously enriched over the NC reservoir. So this corroborates that this dichotomy is a ubiquitous characteristic of the entire meteorite record. And it's not only seen for titanium and chromium and molybdenum, but it's now also seen for many different other isotope systems. So it's a very fundamental observation when we look at our meteorite record. So what does this now mean? Why is this relevant? And for this, it is useful to again include the other component that I talked about, and these are timescales. So if we link these genetic signatures with the lifetime of, or the timescales of meteorite parent body formation, and then we can maybe say something about the formation and lifetime of these reservoirs. And for this, it's useful to determine the accretion times of NC and CC meteorite parent bodies. Now, for that purpose, we need to use two different approaches. For iron meteorites, as we've already discussed, we need to determine the time of core formation. And we found already at the beginning of this talk, as I discussed, that accretion of these parent bodies occurs within less than 1 million years after CAIs. However, for chondrites and primitive meteorites, we cannot use this approach. And what we instead do is we try to date, or we date, the most prevalent components in these primitive meteorites. And these are known as chondrules. And these are basically small spherules, melt droplets within these meteorites. They're rounded objects. And the advantage is that they can be dated. They can be relatively well dated using different chronometers. Now let's have a look at this. And I basically show you just a summary diagram for different chondrule ages that have been obtained over the last, say, 2 decades. And this is for different chondrite groups, for ordinary chondrites from the NC reservoir, and for carbonaceous chondrites, in this case CV and CR chondrites from the CC reservoir. And shown are data for different chronometers, for the aluminum magnesium system, another short-lived system, for the hafnium tungsten system, and the lead-lead system. And you see that these ages agree relatively well. And based on this diagram, we can conclude that chondrules formed between 2 and 4 million years after CAIs. I know, and maybe some of you noticed, that there is some discussion about this, because if you look at individual chondrules, some of these chondrules are even older than this time interval, and maybe as old as iron meteorites or as CAIs. But I think this diagram, because this is for bulk chondrites, it is pretty clear that the majority of chondrules of these meteorite groups, they formed relatively late in the evolution of the solar disk, so between 2 and 4 million years after sea ice. A consequence of this is that the NC and CC chondrite parent bodies, so the parent bodies of these chondrules cannot have accreted before that time. You first have to form the component, and it can only then combine these components to form a parent body. So this must mean that the NC and CC parent bodies formed between 2 and about 4 million years after sea ice. Now let's combine these observations now for iron meteorites and chondrite, as well as several other groups, into one diagram. And this is what you get then. So this diagram shows you the accretion time for NC and CC meteorite parent bodies. And there's a very crucial observation that can be made here. And this is that in both of these reservoirs, both these genetic reservoirs, accretion was about contemporaneous and lasted a period of time, right? So the blue and the red bars, they overlap over a time interval that lasted several million years. And this very crucially means that these two reservoirs, they do not reflect a temporal separation. They did not just form after the other, but they coexisted within the protoplanetary disk for a period of several million years. That's a basic conclusion we can draw from this dichotomy. Now, obviously, there are some important dynamical implications of this, and this is what I would like to discuss here. The meteorite data indicate the spatial separation of these reservoirs, but this is something that is not easily accomplished. And this is because the protoplanetary disk was characterized by very rapid mixing, both inward and outward mixing of small dust grains. And this mixing would have occurred on much faster timescales than this period of several million years. So you need something that locks in these different reservoirs for an extended period of time. And a few years ago, I proposed that you need some type of barrier in the disk. And what I proposed specifically was that the formation of Jupiter, a gas giant planet, was responsible for this. It's the largest planet of the solar system. It's the closest gas giant planet. And we also know that Jupiter must have formed at some stage in the early evolution of the solar system. So it's only reasonable to assume that it played some role. It has a huge gravitational effect on all the other bodies that formed in the solar system. So this is what I propose. And obviously this is a model. And by now there have also been some other hypotheses that have been proposed. But here we go. So this is what my take on this, on what this dichotomy means for the earliest evolution of the protoplanetary disk. And what we think happened, and this is also combining several constraints from other studies, what we think happened, at least most likely happened, is that the composition of the disk initially was very much like that of calcium alumina-rich inclusions, sea and ice. They are the oldest objects, so their isotopic signatures are probably very similar to kind of a reflection of the earliest disk at 0 million years. But at some point, you need to change the composition of the disk by adding material with a different composition in order to create these heterogeneities within the protoplanetary disk. And by the way, this is a 2D cross-section of the disk with the sun here to the left and the disk kind of to the right here. So what must have happened, and this has probably happened already quite quickly, in a few 100,000 years, is that the infalling material on this disk from the molecular cloud changed in isotopic composition towards a more NC-like composition. And this change in infall, this heterogeneous infall, is the fundamental process that may have led to these heterogeneities within the disk. But then we're not finished because we need something, as I said, to lock in these different reservoirs for an extended period of time. And what I've proposed in a 2017 paper is that the mixing between these reservoirs was blocked by the formation of a proto-Jupiter by the core of Jupiter. Because once this core reached about 10 to 20 Earth masses, it would have basically reversed an inward drift of particles and hampered mixing between these NC and CC reservoirs very efficiently. And what this would then mean is that the NC reservoir basically reflected or represented the inner solar system, the CC reservoir, the outer solar system. And because the iron meteorite accretion times of iron meteor ground bodies are so old, they occurred within 1 million years, this formation, this Jupiter barrier must have already been in place at this very early time within less than 1 million years. And this would then in turn mean that Jupiter is also dissolved. So the core of Jupiter must have formed within less than 1 million years after sea ice. Now, at some point, some additional processing must have happened. To explain the present-day asteroid belt, for instance, we need to have some implantation of these CC bodies into the inner solar system. This happened several million years later. And this can have happened, for instance, by migration of Jupiter, as has, for example, also been proposed in several dynamical models, such as the Grand Tech model. But I'm not going into detail about this today. Now, as I said, this is not a unique model. It is open to discussion and interpretation, and other observations may change this model. There have been some other suggestions that have been made. For instance, it has been proposed that it was not Jupiter creating this barrier, but instead it was a pressure maximum in the disk. This was by a 2020 paper, was suggested in a 2020 paper. And Jupiter would then have formed later at that location. Alternatively, it could be that planetesimal accretion happened in 2 different locations in the disk, inbound and outbound of the snow line. And this has been proposed also in another paper, actually of this year. This is also possible. And the last word about which of these scenarios is correct has not been said yet. What I do think, though, is that to really explain this extended period of separation between the NC and CC reservoirs, you still need something like a barrier to keep these reservoirs separated so efficiently for several million years. So this brings me to the second part of the conclusions, and this is that a fundamental dichotomy exists in the meteorite population, indicating that some meteorites derive from the inner solar system, the NC reservoirs, and some meteorites derive from the outer solar system, the CC meteorites. And this dichotomy reflects a spatial separation between about 1 and 3 million years after sea ice, and in my point of view, likely requiring the early growth of Jupiter. Okay, so that's the first part of the talk, and now we will do the last part. This will take probably an additional 15 minutes, if there's enough time for that. And now we kind of switch topics, and we will discuss how did the moon form, and what can isotopes tell us about this. And this may be a kind of a continuation of a talk that was already given in this seminar, but I will give my point of view about this in the next few slides. Now, you may think, well, this is all set. There's pretty clear, there's kind of consensus in the community that the giant impact hypothesis, that this is the mechanism by which the moon formed. And in this giant impact hypothesis, the idea is that a proto-Earth had largely formed, and at some point it was hit by maybe a body about the size of Mars, the impactor, also referred to as Theia. This would have led to widespread melting of the proto-Earth and this impactor, ejection of material into Earth's orbit, and then from this material the moon would have accreted. Now, this can explain several important observations about the Earth-Moon system, notably the angular momentum of the Earth-Moon system, the iron depletion in the moon, and several other factors. So it's been very successful. It's a very successful model for explaining the origin of the moon. However, it's also not without problems. And this can be summarized by this phrase, the lunar isotopic crisis. There is a bit of a crisis because there are 2 observations that cannot really, or could not really be reconciled for a long period of time. And it comes down to this. It comes down to the fact that the classical giant impact model predicts that the moon largely consists of impactor material, and therefore should mostly compositionally and isotopically reflect that of the impactor. At the same time, though, we observe that the Earth and the moon are isotopically very similar, which is kind of seemingly inconsistent with this. And to reconcile these observations, a variety of solutions have been proposed over the last decade or so. And there are basically three classes, in my point of view, that have been proposed. You could reconcile these observations if we make the moon mostly out of the Earth's mantle and not the impactor. In other words, you would change the classical impact scenario such that the moon is mostly made out of the Earth's mantle, in which case you can naturally explain the similar isotopic compositions. The second solution is that the Earth and the impactor derive from the same reservoir in the disk, so in the solar system. And in this case, you would, contrary to what we've seen for different meteorites, you would not have different nucleosynthetic isotope signatures, like for elements like titanium or chromium or so, but they would simply stem from the same region, and therefore there would not be any isotopic heterogeneity to begin with. And then these observations can also be reconciled. The third option is that there was some mechanism after the moon formed in a giant impact that facilitated equilibration and very efficient mixing between the Earth and the moon, which would have erased any heterogeneities. Now, which of these is correct? That there's still a lot of debate about this, and this has not been entirely understood. And what I would like to show you is how you can use tungsten isotopes, so the system that we've already discussed in the context of iron meteorites, how you can use this to test different giant impact scenarios. And tungsten isotopes are quite useful for this because, as we discussed, contrary to nucleosynthetic isotope variations, the variations we see in 1A2 tungsten are mostly resulting from core formation. They ultimately result from the fact that core formation caused the mantle and cores of bodies to have very heterogeneous 1A2 tungsten compositions. Now, we've already seen some of this, and this is summarized also in this diagram here to the right. Iron meteorites have very unradiogenic, very low 182 tungsten composition because they stem from the cores, much lower than chondrites, and also lower than the present day Earth's mantle, the bulk silicates Earth. In contrast, crust and mantle-derived samples like angrites and eucrites have very high and very variable 182 tungsten variations, indicating that they stem from the mantle, which has a high hafnium-tungsten ratio. So, what you can also consider that in this classical giant impact scenario, the moon must have been a random mix of about three components, consisting of impactor mantle, impactor core, and proto-Earth mantle. And each of these components have distinct 182 tungsten composition due to core formation. Now, these components, as I said, were randomly mixed during the giant impact. So if you think about it, if you kind of qualitatively think about this, it must almost be, it is almost inevitable, or it would be very fortuitous if the Earth and the moon ended up with exactly the same isotopic compositions in tungsten isotopes. So it's much more likely that you would find a significant tungsten isotope anomaly in the moon resulting from the giant impact, simply because this is more or less random mixing of highly heterogeneous 182 tungsten compositions. So you may ask the question, do the Earth and the moon have different 182 tungsten compositions? Now, how do we assess this? We can simply measure the tungsten isotopic composition of lunar rocks, that have been collected on the moon during the Apollo missions. And I'm taking a few leaps here, but this is basically the summary plot. And these are the tungsten isotopic composition of different lunar source rocks. Now expressed not in the epsilon unit notation, but in the so-called mu notation. And this is the parts per million deviation relative to the terrestrial composition, instead of the parts per 10,000. And what you see is that different lunar source lithologies, including high titanium and low titanium Mara basalt, magnesium sweet rocks, creep-rich samples, they all have a significant tungsten isotope anomaly relative to the present-day bulk silicate Earth. So different rocks, different source rocks on the moon, and this result has also been reproduced in 2 different labs and using different mass spectrometry techniques. So this is quite robust. We know that the moon is enriched by about 26 parts per million over the present-day bulk silicate Earth in 182 tungsten. This, by the way, also means that the source regions of these rocks, because they had different hafnium-tungsten ratios, they formed after extinction of the system, meaning that the hafnium-tungsten system basically requires that if the moon had a magma ocean, that it differentiated so to say, relatively late, more than 70 million years after CAI formation, but that's more of an aside. So what does this result mean? What is the origin of the small excess in the moon? Well, it could mean that we have observed that there is a significant radiogenic difference between the moon and the Earth. And this would mean that you're basically, that is a reflection of the fact that the moon formed when 182 hafnium was still alive. So one possibility, it would mean that the moon is relatively old. A second possibility is that, as I just discussed a few slides back, that indeed the moon shows a signature from the impactor. But before we can conclude any of this, we also have to assess another process, and this is referred to as late accretion. And late accretion is the addition of materials to the mantles of bodies after core formation had ceased. And for the Earth, we know this is also referred to as the late veneer. We know that about 0.5% of the Earth's mass was added after the end of core formation by late accretion of materials with on average chondritic compositions. Now, what is also important in that regard is that we also know from highly certified element abundances that the moon had much less late accreted mass. So late accretion occurred on both bodies, but it was disproportional. And this by itself can create a tungsten isotope difference. Now, how this works is shown here in this diagram. This is a mass balance calculation, and this shows you the effects of disproportional late accretion on the Earth and Moon. And for this, of course, you need to make several assumptions, and therefore the result is relatively uncertain. But what you can do is take the present day bulk silicate Earth and subtract the effects of late accretion. And what you then end up with is a significant positive anomaly for the pre-late accretion bulk silicate Earth. And this composition overlaps with the value of the Moon, also when late accretion is taken into account. So this proportional late accretion can fully account for the small excess in 182 tungsten in the Moon. And this means that the pre-late accretion bulk silicate Earth and Moon are indistinguishable. This then also means that, and I will skip this slide for now, this then also means that the Earth and the Moon had very similar 182 tungsten at the time of the giant impact, and that any effects of, or that neither radioactive decay nor the giant impact itself induced the tungsten isotope difference. To the very least, we can say because this pre-late accretion composition of the Earth is relatively uncertain, there is no resolvable difference remaining once these effects are taken into account. You simply cannot prove that there would either be a radiogenic difference or a difference resulting from the giant impact. So what does this now mean? Can the giant impact account for this observed tungsten isotope similarity? And this is what I will discuss now in the last few slides. And for this, it is useful to assess the probability of producing these very similar isotopic compositions in the context of known giant impact scenarios. And that's what we do here. And what I did was I simply calculated the predicted tungsten isotope difference between the Earth and the Moon in the context of these different giant impact scenarios by mixing variable proportions of proto-Earth mantle, impactor mantle, and impactor core, which all have these different 182 tungsten compositions. Now, there are many factors involved here. So many parameters like the degree of metasilicate equilibration, partition coefficients, impact of the Earth ratio, and so on and so forth. So it's a non-unique problem. You cannot just solve this, but you can use statistics to see what this means and what the effects are when you mix these together. And when you do that, and this is done in a Monte Carlo simulation, you end up with this result. This is a plot of the predicted tungsten isotope composition of the Moon and hafnium tungsten ratio of the Moon for two different scenarios. A classical impact scenario and a scenario which is being more prevalent in kind of these modified impact scenarios where the Moon mostly consists of the Earth's mantle. And what you see is that in both cases, for the composition of the Moon, you generate a very broad field of composition with very different 182 tungsten compositions. And in many cases, a significant excess in 182 tungsten relative to the Earth, which would be here at 0, is produced. And if you then plot in the observed Moon, you see that it only plots somewhere along the edge of these distributions. And this is consistent with a very small probability for matching that composition. This has also been reproduced in another study by Fisher et al. Using more sophisticated models for this. And the conclusion is that it's a very small probability situation to get exactly the same tungsten isotope compositions between the Earth and the Moon. By contrast, a significant tungsten isotope difference is predicted in most giant impact scenarios, and the probability of producing similar tungsten isotope compositions is only a few percent or less. And this is the case even if the Moon consisted mostly or fully out of proto-Earth mantle. So what is now the solution to this? Because we're still left with a conundrum to a degree. Why do the Earth and the Moon have similar 182 tungsten compositions? And I can think of 4 possibilities, and fortunately I don't have the final answer to this, but these are the 4 possibilities I can come up with. One option is that indeed there was, as I already mentioned as one of the solutions at the beginning of this part of the talk, that the giant impact facilitated efficient isotopic homogenization. And this could, for example, be accomplished in so-called high energy, high angular momentum giant impacts, for example, in a synestia. The second possibility is that the value we measure for the Moon, the isotopic compositions we measure in Apollo rocks, are not representative for the Moon at the time of the giant impact. This could be the case, for instance, if a large impact, for example, on the near side of the Moon, modified the isotopic signatures of lunar rocks. A caveat with this is that you would basically also change any other system, any other rock, or the isotope systems in other rocks that are measured. So it's a bit of an ad hoc explanation. And it would maybe mean that even the very rocks, lunar rocks that we use to study, say, the lunar magma ocean processes, they would also be affected by such a large secondary basin. So that's also not so satisfying. It could be that the probability is in fact increased for this to happen if we can independently show that certain conditions prevailed during the giant impact. For example, a certain oxidation state, or a certain size of impact, or a certain energy of the impact. This would narrow down maybe this compositional space that I just showed you, and may make it more realistic that the Moon and the Earth ended up with the same composition. And a final option is that the giant impact model itself is simply incorrect, and that we're looking at it completely the wrong way. But of course, then you would have to ask yourself, what is the alternative, and are these alternatives more likely? Okay, so I'm reaching my conclusions now. I've been talking for about 50 minutes, I realize. So the conclusions for the last part of the talk is that the formation of the Moon probably involved a giant impact, but the details remain hotly debated. Pre-late accretion, bulk silicate Earth and Moon had indistinguishable 182 tungsten. And this similarity in 182 tungsten poses a critical constraint on current lunar formation models. Thank you very much for your attention. Open for questions, of course.
Yeah, thank you so much, Thomas, for this very, very, I would say very comprehensive, presentation on this on new findings, many new findings. And anyone in the audience want to ask Thomas, Professor Kruijer, questions first? If you do, please unmute yourself. I myself have a few questions which I want to like to know. I mean, some of the things that may be very, very simple and easy to answer. In one slide, I mean, you mentioned that actually in the last summary, you mentioned that the iron meteorite formed early within, within 1 million years to the CAI, right? Is that because of the aluminum-26? Because this happened to both for the carbon chondrite and CC and NC,
Yeah, so I do think that, I do think that I understand your question. It is.
Because you in your distribution you point you have this iron meteorites formed younger than 1 million years after.
Yes.
Yeah. Say all right.
Yeah. So if I understand it correctly, I think you're alluding to the fact that why are these differentiated, these core direct materials, why are they the oldest? And that is, in my point of view, indeed because alumina 26 decay, if a body formed early, then it would have been melted by alumina 26 decay, by radiogenic heating. And for that reason, you kind of naturally see that the bodies that accreted later, they are the unmelted bodies, but because they never had a chance to meet, because there was no alumina 26 left at that late time. And for that reason, you see that the oldest bodies, they are the differentiated ones. This, of course, must in turn also mean that in principle, you could also find bodies that are very old, that are undifferentiated, but we simply don't see that anymore, these undifferentiated natures, because the melting has already occurred, if I'm saying that correctly.
Right. So therefore, the iron meteorites could have formed in bodies very small, right? I mean, even 20 kilometer, 30 kilometer, you could form iron meteorite.
Yes. Yeah. So it's there is a kind of a minimum size. So you may kind of, if a body is too small, it is not big enough to retain the heat from alumina 26 decay. And in that case, it would remain undifferentiated. But indeed, yeah, even a body, I think about 20 to 40 kilometers in size would heat up sufficiently for complete melting to occur.
Can the isotope analysis say something about the orbital migration scenario, like the Grand Tech model? You say you don't want to talk about that now, but you might have thought about that.
Yes, yeah. So that's, I do think in principle that the isotopic constraints that we have, not only what I presented here, but this dichotomy in general is fully consistent with a scenario like the Grand Tech. Because this early, also the Jupiter model would be, because this early growth of Jupiter would have naturally led to implantation of CC bodies from the outer solar system into the inner solar system. So in fact, and this would also, this early growth of Jupiter would also have led to migration. So this can kind of naturally explain why we see that present day, why the asteroid belt that we have today has the current structure that it has, why it's relatively mass depleted. So it would be consistent. And if these results are correct, then it would mean that the Grand Tech would have happened, say, about 4 million years after CA ice. Mm-hmm. So after the accretion of meteorite parent bodies was completed in also in the CC reservoir. But of course, the details are very uncertain. That's true.
Yeah, actually, I would have liked you say that. Oh, it's not consistent. You know, that would be very interesting.
Yes. Yeah.
Well,
well, I would say that the Grand Tech is only one scenario. I think there's considerable debate about which model for the early solar system or migration model can best explain all the observations.
The last question is that you seem not to have that. You seem to have no objection to this new model of synestia.
Yeah, so I do think that the synestia model can, in principle, explain the isotopic similarities. It is the question, of course, remains is how likely this scenario, this model in itself is. How likely is it? Because I think, especially with these questions regarding the origin of the moon, you very much have to talk in terms of likelihood of a given scenario, and you have to wonder, because it's a bit of a one-off event. Is the formation of the moon, is the giant impact, is it likely that it was characterized by synestia? And I think there is still some debate about that. But in principle, if the synestia happened, it could facilitate this homogenization that's needed to explain the isotopic similarities. I would still place the caveat there that you need very, very, very efficient isotopic homogenization, because the isotopic difference, we really see isotopic similarity on the 10 parts per million level. So you need a very efficient mixing process, I think.
Very good. I mean, this I learned a lot, from your lecture. I hope that your lecture will be archived. I mean, that we have made the record and put on. There will be posted on the web page for people to to see, and maybe a couple of years later we will come back and to watch it and to see whether you are completely correct or 99%.
That's a good. There are probably some things that are completely wrong, but that is normal. That is science.
Don't worry. Okay, good, Thomas. Thank you so much. Yeah.
I would have a question for
Have a good day. Thank you.
Thank you.
Could I ask a question?
Oh yeah, please.
Yes. 1 second. I will turn on my camera. Hi.
Hi.
Can you hear me well?
Yes. Yeah.
Perfect. First, dankjewel, Thomas. That was a super interesting lecture. I'm Max Malke from the observatory in Nice, France. And I'm a PhD student and I work on asteroids. So naturally, my question is going to be about asteroids a bit. And you just mentioned that asteroids are mostly used to study the dynamical evolution of the solar system so far, because clearly we don't have the chemical knowledge that we get from the isotopes and meteorites. But we do have a much more complete overview of the asteroid belt than our meteorite collection, which might be lacking important pieces. So I wanted to ask if, in your opinion, the chemical information that we do have on asteroids could also be useful to study the genetic and not only the dynamical evolution of the solar system.
Yeah, in principle, yes, I would say. It depends a bit on which approach you would take. But I think, yeah, as you say, I think the chemistry also, there's definitely a subfield in cosmochemistry that tries to kind of, for example, link meteorites to a particular region in the asteroid belt. And I think if you use modeling constraints, you can also use the present-day structure of the asteroid to kind of to reconstruct where bodies may have formed. So in that sense, yeah, I think you can say something about the structure also of the asteroid belt. I will place, well, I would say, I do think that these nucleosynthetic signatures, which kind of require lab analysis of meteorites, they are very compelling as genetic tracers, because they very precisely can tell you if something belongs together or if it doesn't belong together. Of course, the disadvantage of that approach is that even though I'm claiming this, that we know where we can pinpoint materials, at face value, when you just measure an isotopic composition in a meteorite sample, you cannot know that it's exactly derived from a particular location in the solar system. So there's always some interpretation associated with it as well. So probably the real answer is that you need some combination of different approaches to try to pinpoint where materials came from. And I think it is very important that the modeling community works together with the cosmochemistry community to kind of arrive at the best possible estimates for that.
All right, thank you very much.
So maybe I follow that up. So Matt, no, I mean Thomas, what do you think of the how important is the sample return mission from asteroids? I mean, seems that you know everything from meteorite samples, and why should we go to asteroid to collect samples again?
Oh, I think it's very crucial that sample return missions happen as well, because I think basically if you're interested in learning about the early solar system, and that you kind of course, this is all blue skies research. It is an interest in our own origins. It's an interest in how the planet Earth formed, how the solar system formed. But if you're interested in that, it's very important that we learn new things and that we also explore the solar system. And progress in my field, in isotope cosmochemistry, is mainly made either by analytical advances, so technique advances, and the second ingredient is access to new samples. And a lot of the samples that we have in our collections have been pretty broadly studied at this stage. And we know, for example, also from the past, when when the Allende meteorite fell on Earth, and when the Apollo missions happened, the access to these new samples that have been collected, or either meteorites that fell on Earth, that has provided a wealth of new information, and basically that can revolutionize the field if you have new sample materials.
Mm.
So I think it's absolutely crucial to obtain new samples from using sample return missions, even if it costs some money.
Even costs some money. There, yeah. Well said. But you know, the asteroids, there are many types of asteroids, right? We could not afford to go to all of them. So then for instance, you talk about CC and NC, presumably you have also the meteorite, the asteroids corresponding, asteroid type. So you have only money to go to one kind of asteroid to collect sample. Which type would you go? So in asteroid terms, you talk about C type or S type, right? C type, S type asteroids, you know that, yeah. So which kind?
Yeah, that's a very good question. I would have a hard time choosing.
I mean, for now, like the Lugo and also the Bennu, they go to this B type because they think it's the most primitive. Yeah, even C type. So now you have a second chance. What would you do?
Well, I'm very interested, for example, in the Psyche mission, the mission to a metallic type asteroid. But that also is because kind of in my research field, I'm very interested in core formation and metallic cores. And this is the first time we would actually go to an asteroid like that, or get such detailed insight. I do think probably for the broader field, we'll learn most new things if we study materials that are unlike anything we see in the meteorite collections, and that may be more material from the outer solar system. So more CC type asteroids, or very primitive asteroids that will show us things that we cannot learn from the meteorite collections that are available on Earth, or that are at our disposal so far. So yeah.
So you'll be advocating a sample return mission to comets.
Yes, that would be very interesting, but not so easy, of course. Another thing, what I think, and what is not often discussed, but what would be very compelling, is to have a sample return mission, for example, to a planet like Mercury, and see because we basically only have materials from the Earth. Obviously, we have rocks from the Earth. We have materials from Mars, but not from Venus or Mercury. And if we had a good sample set from either of these two planets, not that easy, I know, but that would also completely change the way we think about planet formation, I think.
Yes, Thomas, I say that you're still very young, so I believe that you will have a chance to convince ESA to have a sample return mission from Mercury.
Yes, maybe that will be the second part of my career, maybe.
Okay, good, very good. Yeah. Thank you so much, Thomas. Yeah.
Yeah, you're welcome.
Yeah, bye-bye.
Okay, bye-bye. Bye.